Hey, this is Mr. Roark. This is the video review for Unit 10, Nuclear Physics. So we'll go over structures of an atom, we'll look at radioactivity, nuclear fission, nuclear fusion, and of course we'll look at rates of radioactive decay. One thing you got to be able to do in Unit 10 is to follow a decay series. So let's start out with a common isotope, uranium 2. Oops. Mass has to go on top. Uranium-235. Uranium has 92 protons. And so I'm just going to make this up. This won't be realistic. It's not a real decay series, but we can do it the same way. So let's say it has an alpha decay, and then a beta, and then a beta. So put commas in between there. And then I'll throw a gamma in there, and then another alpha, and then another beta. What we want to know is what is the final product? What is the final daughter nucleus? Now you could draw out equations for every single one of these things, but that'd take a lot of work. If you understand what happens in each of the types of radioactive decay, it makes it a lot easier. We can just do it using algebra. So first, we know that an alpha decay releases 2 protons and 2 neutrons. So for every alpha decay, you actually have a chunk that breaks off. And we give it the symbol of a helium nucleus because it is 2 protons and 2 neutrons. So we're not going to write the helium nucleus here because I don't want to confuse people. Let's just put 2 protons and 2 neutrons. So every single alpha decay, this starting product right here is going to lose that amount. So after the first alpha decay, it's already lost 2 protons and 2 neutrons. And as we go through, we got another alpha decay over here. It's going to lose 2 more. We can use simple algebra to figure out what's going on here as far as the mass and the number of neutrons. Let's start with the mass. The mass is 235. So let's write that down here. For each alpha decay, you lose a total of 4 things, 2 protons and 2 neutrons for a total of 4. So for the first alpha decay, you're going to lose 4. And for the second alpha decay, you're going to lose 4. Okay? So after our alpha decays, the 2 alpha decays here and here, we're just kind of combining those because it doesn't really matter what order these things go in for the total effect. The total number of alpha decays means our mass is going to decrease by a total of 8. And so 235 minus 4 is 231, minus 4 is 227. So our alpha decays have changed our mass to 227. What about the number of protons? Well, the alpha decay is going to reduce the number of protons by 2 each time. So if we start with 92 protons, we're going to lose 2 from this alpha decay. And we're going to lose 2 from this alpha decay. So we're going to lose a total of 4, which gives us 88. So far, just by looking at the alpha decays, our mass is 227, and our number of protons is 88. Now what about the beta decays? Well, what happens in a beta decay is a neutron turns into a proton. Now because the total number of nucleons, the total number of things in the nucleus doesn't change, that means the mass doesn't change appreciably. So the beta decays don't affect this mass number at all. So we can leave that alone completely. For the number of protons, though, because a neutron turns into a proton, that does change the number of protons there. So for every beta decay, we're actually going to add 1 proton on because it's coming from one of the neutrons. So for this beta decay, we add 1. For this beta decay, we add 1. And for this beta decay over here, we add 1. So we started with 88. We got 3 new protons, which gives us a total of 91 at this point. So the beta decays didn't change the mass at all. We had 3 beta decays, so they increased the number of protons by 3. We ended up with 91. The only thing we have left is our gamma decays. But a gamma decay is just a release of energy, pure radiative energy from the nucleus of the atom. So there's nothing that changes about the structure. The number of protons and neutrons overall doesn't change, and we don't have anything that's converting from one to another. So that means the nucleus doesn't really change, which means when you're looking at a decay series, those gamma decays don't matter at all. You could have 24 gamma decays in there, and it wouldn't add to what's going on. So if you look at it from this light, only the alpha decays can change the mass. So the 227 we got only by looking at the alpha decays. So when you're doing a decay series, you can just add up the number of alpha decays. In this case, we had 2. And then for each one, we're going to lose 4 from the mass. So we end up with a mass of 227. So let's see, let's write our answer down here. For the number of protons, you have to look at the alpha decays and subtract 2 for each one. But then you have to add 1 back on for the beta decays. When we did that, we got a total of 91. And because we changed the number of protons, we're not looking at uranium anymore. We have to look at the periodic table and see that number 91 is pronacneo, the symbol Pa. And this will be the overall daughter nucleus. Okay, in Unit 10, you have to be able to write equations for each type of radioactive decay. So I'm just going to put the types over here. We got alpha decay, we've got beta decay, and we've got gamma decay. We need to write equations for each of those. So it's really a good idea to understand what happens in each of the decays to be able to write the equations. In alpha decay, no matter what we start with, in fact, I'm not even going to put a starting material down here right now. No matter what you start with, when that thing goes through alpha decay, you get 2 protons and 2 neutrons that break off. We call that an alpha particle because it has the exact same configuration as a helium nucleus. We use this symbol. So this is the alpha particle that comes out. That's the thing that is the radiation that can cause damage to your cells and whatever, and it does that because it has an overall positive charge. But in every single alpha decay, you will always get out that alpha particle. In every single case. So if you're looking at an alpha decay, you could write that down right away. You don't even have to know what you're starting with. It doesn't matter what you're starting with. You're going to get that thing out. Now, what about for a beta decay? Again, let's ignore what we're starting with and just take a look at what comes out in a beta decay. Of course, we know a beta particle comes out. The beta particle is the thing that is the radiation that can cause damage to you, but a beta particle is simply an electron. So we just use the symbol for an electron. But this is the part that most people forget. There is another particle that comes out, a newly discovered particle. It was newly discovered after they started understanding how beta decay worked, and we call it a neutrino. It's tiny. It's even smaller than an electron. It doesn't have a charge, so it can't hurt you. But even though it's basically insignificant, because it comes out, it's still one of the products of the nuclear decay, and we have to include it in the equation. For the neutrino, we use the Greek letter nu, which kind of looks like a B. I want to just put a 0 up there to show that it is neutral. Every single beta decay that we're going to look at releases that beta particle, the electron, and that neutrino. So again, that's something that you can write down in every single case. What about a gamma decay? All gamma radiation is energy. It's a release of energy. So because it's not a particle, we don't have a particle symbol for it. So to show that gamma wave, we just use the Greek letter gamma. This is electromagnetic radiation. It can knock electrons out of your cells, which is what hurts you. This is a negatively charged particle. It's what can hurt you because your cells can grab onto it and become ionized. This is a positively charged particle. It can hurt you because it can take electrons away from your cells, which can hurt them. These are the things that are the actual radiation. They come out from the nuclear decay, they spread out, hit things that get in their path, and can cause trouble. But of course, the other part of doing the equations is figuring out what the daughter nucleus is, what else is produced in the reaction. But to do that, you have to also know what you're starting with. So let's take a look at an isotope of plutonium. Let's look at plutonium-244. Plutonium always has 94 protons in every single case. So let me just clone this. We'll look at how this changes in each one of these decays. All right, alpha decay. The number of protons is going to decrease by 2. You started with 94, but you're losing 2 of them. That means on the other side over here, the daughter nucleus now only has 92. The mass decreases by 4. You started with 244, but you lost 4. That means you're only left with 240. Because we've changed the number of protons, that changes our element. We look at the periodic table and we say, what has 92 protons? Oh, that's uranium. So the daughter nucleus in this case is uranium, specifically the isotope uranium-240, or U-240, we sometimes say. What about the beta decay? Well, the electron and the neutrino have tiny mass. In fact, their mass is so small that it doesn't change the mass of the atom significantly. So the mass on the other side of the daughter nucleus is still 244. But because in this process, a neutron has turned into a proton, now we don't have 94 protons, we've got 95. And again, because that has changed, we have to look at the periodic table. 95 would be americium, which is found in smoke detectors. Okay, now what about gamma decay? Gamma decay is kind of the easiest one because the nucleus doesn't actually change. The parent nucleus and the daughter nucleus have the exact same configuration. So it's still plutonium-244. But we can't have the exact same thing on each side. Where did this gamma ray came from? Where did this gamma ray come from? Well, it came from extra energy that was in the nucleus of the atom. And we have to show that there was that extra energy there. And all we do to show that is just to put a little asterisk there to show that it was in an excited state and release that energy, and now it's not excited, so there's no asterisk on the daughter nucleus side. Now, when you're looking at this, you really just need to memorize what comes out and figure out how the nucleus of the atom changes, because, of course, I could give you any specific isotope. I could give you radon-220, and you'd have to figure out how that's going to break down into each of these, in each of these different decays. But once you look at the process and figure out how it works, they all work the same, and it really becomes fairly simple to be able to write those equations out. Good enough.